So here's another problem. This one has to do with characteristic subgroups, and this problem says, let G be a group. Show that if H is a characteristic subgroup of N, and N is a normal subgroup of G, then H is a normal subgroup of G. So let's go ahead and get started. So proof, and we're going to suppose that G is a group, and N is a normal subgroup of G, and H is a characteristic subgroup of N. So subgroup of N. Okay. Now, before we keep going, let's remind ourselves what it means for a subgroup to be characteristic. So definition: a subgroup H of G is called a characteristic subgroup of G if phi of H is equal to H for every automorphism of G. So for every automorphism of G. Now let's also remind ourselves of a fact. I don't have a proof of this uploaded. I'll probably do one. So fact, for a fixed G in G, the action of conjugation is an automorphism of G. The action of conjugation, we'll say by G, is an automorphism of G. This will be very useful here. It's an automorphism of G. So let's go ahead and define this action. So define this action as the function, and we'll call it phi for convenience, phi mapping G to G with phi of X being conjugated by G. Now let's use the fact that N is a normal subgroup of G. So since N is normal in G, it happens that this action here is also an automorphism of N. This action is also an automorphism of N. But since H is characteristic in N, then H remains invariant under this action. So let's write this down. Hence, H is invariant under phi for all G in G. And let's write exactly what that means so we can show that this essentially completes the proof, right? That is, phi of H is equal to GH G inverse, but this is an automorphism of N, so this is equal to H, and hence H is normal in G. I've seen some other variations of, not, I guess not variation, but a similar statement to this, where it'll say something like, let me copy this down. Copy. So I've seen iterations of this kind of problem where instead of n being normal, n is a characteristic subgroup. So it'll say something like this. Oh, you know what? Didn't grab that right. Where it won't say that n is normal, but it'll say that this is a characteristic subgroup as well. And if this is the case, then you just have to remember that since n is characteristic and the action of conjugation by G is an automorphism of G, then you can use this fact here to show that n being characteristic implies that n is also normal in G then. And then, we just kind of prove this here, this statement, that if it is normal, then H has to be normal as well. So it's just changing one of the assumptions just by a little bit, but the result is still the same. H is still a normal subgroup of G. So this completes the proof, and we're done.